We're going to finish the year doing 2 units. It might end up being 1.5, looking at magnets and magnetic fields. I love magnets. What kid doesn't like magnets? What kid is not fascinated by this weird metallic looking thing that pulls on something else and exerts a force? We all find magnets cool. A few years ago, I made a dumb mistake. I handed out the magnets to my students, and then I started teaching. I lost them for the whole lesson. So I will let you play with these later. I will say these are strong magnets. These are quite strong magnets. How strong are they? Strong enough that... Go through my hand? Should go through my hand. Usually does. Yeah. Okay. What that means is I'm very cautious about where I put them. Don't absent-mindedly put these in your pocket next to your smartphone. Be a bad thing. Okay? You can do some nice witchcraft. Behold, move, move, right? And if you're not careful, they can really pinch your fingers. These are small, rare earth magnets. They do make them bigger and better. Magnets, it turns out, are dipolar. The same way charge comes in 2 types, positive and negative. Magnets are dipolar. They come in 2 poles. Anybody know what we call the poles? You do. North and south. So a standard magnet might have a north pole and a south pole. Okay. Very similar to charge, like poles repel. Opposite poles attract. However, unlike electric charges, it's impossible to completely isolate a north pole or a south pole. You can completely isolate a positive charge. We call that a proton. You can completely isolate a negative charge. We call that an electron. And yeah, we can go into quarks, small, but there is you can break it down. It's impossible to isolate a north pole and a south pole. What would happen if we cut this magnet in half? If I broke that magnet in half, that would become north and that would become south, and I'd have 2 smaller magnets. Okay. Magnets send out magnetic field lines, similar to electric field lines. I went on my rant, Jason, about action at a distance. I said you're not allowed to move something or apply a force to something without touching it, but it is very obvious when I get close to here that there is a force, yet I'm not... Okay, too big a force. It yanks down right away. Well, here, you guys can see the magnet, you guys can't, but certainly I didn't touch it, and I clearly exerted a force. Kohei can't see, so Kohei will do it on my hand here. Behold, right? Da 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 da. Did I touch it? No. Yes, I did. I just touched it I touched it invisibly with a magnetic field. So the same way we said that we could explain how electrical charges could act on each other over great distances by sending out, like the invisible tentacles of an octopus, an electric field. Turns out magnets send out, like the invisible tentacles of an octopus, a magnetic field. Similar to electric field lines. What that means is they're vectors and they have a direction. Remember, for electric field, we had to define the direction. We said for electric field, we'll define it which way a positive would want to move. The direction for the magnetic field is defined as they point from north to south. Or, in terms of a compass, a compass points south. Wait a minute, Mr. Dewick. I was part of Boy Scouts. You're telling me a compass points south? I think you're wrong, Mr. Dewick. A compass points north, Mr. Dewick. No, compass points south. Mr. Duick, I hate to disagree with you, but I've gone hunting in the woods. Pretty sure a compass points towards the North Pole. It points to the geographic North Pole, but a compass points magnetic south. What? This is what the Earth looks like inside. Works a little better if the photo goes a little faster. Really? Is the photo not going to display now in my new photo? Okay. That's a downer. Let's try the other one. Do I have something here? Earth magnet. This is what it looks like. Inside the Earth at the geographic North Pole, there's actually a magnetic South Pole. And that's why a compass, which has a magnetic north on its end, will point towards the geographic north, because that's where the Earth's magnetic south is. That's what the Earth looks like inside. And it's sad because we're very sloppy. We talk about geographical north, and we do talk about magnetic north being up in the North Pole. There is actually no magnetic north up in the North Pole. It should be magnetic south. But that would freak out non-physics nerds, so okay, we live with it. Symbol for magnetic field. Can't use M, mass. So, capital B, from a Latin word, I think. Units, the second last new unit that you'll learn all year. Magnetic field is measured in Teslas. Symbol, capital T. Earth's magnetic field, well, it varies in strength, but it's around 10 to the negative 5-ish Teslas. That's enough to move a compass. A very large magnetic field, a really large magnetic field, one that might even be fatal to a human being over long-term exposure, because it would probably affect the iron in your hemoglobin in your blood. That's massive. Put your pencils down. Okay. Not all, Kiowa, so you asked what about people that have feelings? Not all metal is magnetic. Okay. There are two main types of magnets. I'm starting now. Permanent magnets, like my rare earth magnets, are also called neodymium magnets. They're called ferromagnetic materials. Psst. But even better, electromagnets. This is a magnetic field caused by a current, and in fact, that's what we're going to be talking about the most during this unit. This is really useful because that gives us a magnet that we can switch on and off. And if you don't think that's handy, in fact, not only does it give us a magnet that we can switch on and off, that gives us a magnet that we can make stronger or weaker by changing the current. And hopefully, after the circuitry unit you've clued in, we can really control current quite well. What resistor do you put it through? Change the current. What do the magnetic field lines look like around a single magnet? Remember I said magnetic field lines point from what to what? You have to memorize that. I'm going to write it here from north to south. See the arrows? Pointing from north to south. Also, it's the direction that a compass would point if you placed it in this diagram. If you put a compass right here, it would point like that. If you put a compass right here, it would point like that. If you put a compass right here, it would point like that. And so they'll either ask you, hey, what direction is the magnetic field? Or Raj, just to take it one step further, they might just say, which way would a compass point in this location? They're really asking you, which way is the magnetic field? Magnetic field lines have no beginning and no ending. Inside the magnetic field line actually flows that way, inside the magnet. So it goes in, I can't call it a circle, kind of an ovally shape. They have no beginning and no ending. The Earth is also, sorry? Outside. Yes. But inside the magnet itself, we've got to pick it. We've got to pick a frame of reference somewhere. So, yeah. Earth is also a magnet, which is how a compass works. At the North Pole, what does the magnet inside the Earth look like? That. And that's why a compass, which points from north to south, points to geographic north, because up at the geographic North Pole, there happens to be a magnetic South Pole. Draw the magnetic field lines below. What two poles, Vikas, are closest to each other, are facing each other? Which two poles are closest to each other, facing each other? Like poles. See? So the magnetic field line would start out like that, get repelled, it would come this way, and it would point from north to south. From north to south. Also on this guy, from north to south. You could add some smaller ones. Also down below. Inside the magnet is different, but that's inside. We're not going to look at that. Okay. Well, really, they look like this. Symbols, this is important. Mitch, this is important, so stay off your phone. Put it away. We must end up drawing three-dimensional pictures on flat pieces of paper. So we've evolved some symbols over the years. This symbol here, a circle with an X, that's meant to represent the tail feathers of an arrow going away from us. We see the tail feathers. That's the symbol for into the page. In other words, that would be straight down on this piece of paper, or into the page if I was holding the piece of paper this way. We're going to use, that's meant to be the tip of an arrow coming out of the page towards us. Okay? Sometimes you'll even see they'll not even bother doing the circle. They'll do a bunch of X's just because it's easy to type X's if you're typing. Or they'll do a bunch of dots just because it's easier to type dots if you're typing. I'll do that occasionally. That's meant to say into the page or out of the page. Okay? You have to memorize that, but you'll use that quite a bit. Electromagnets. It turns out that if you send current through a wire, it generates a magnetic field. Any wire that carries current generates a magnetic field. In other words, if you put a compass near a current-carrying wire, that compass will be deflected. And the question we want to ask is, what direction? What direction? Turns out you can figure it out using your right hand, using something that we call the right-hand rule. Actually, there's going to be 3 of them. 3 right-hand rules. And in terms of a current, back. The recording's running, but that's okay. Let's imagine that this is the wire. We're zoomed in like crazy. So imagine you've zoomed in and this copper rod is a wire. And let's imagine the current is going that way. To my left, to your. All of you get your right hands out. Put your pencils down. Here's what you do. Like you're hitchhiking, point your right thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. So for me, closest to you, which way is the magnetic field pointing? Down. Underneath the wire, which way is the magnetic field pointing? Towards me, away from you. Behind the wire, which way is the magnetic field pointing? Straight up. Above the, you know what, let's just do that. Above the wire, which way is the magnetic field pointing? Towards you, away from me. Okay? This is why I said we're going to have to go 3D. Okay? This is the rule for a current carrying wire. Right thumb, not left thumb, right thumb. Do not try and do this while holding a pencil. Please trust me. Put your pencil down. And don't try and do this all in tight. Get your hand out. Trust me, I've taught this before. You don't want to try and do it in close. You'll screw up. Okay? Here's a wire. It's carrying current. What does that X mean? Which way, what direction is the current? Into the page. All of you right now, lift your notes up and hold them like this, just so you match my screen, because my screen now is in the same orientation. Okay? Straight up. Point your right thumb into the page. I would point my right thumb like this. What's the magnetic field on the top? What direction is the magnetic field? Above the wire, what direction is the magnetic field? To the right. Beside the wire, what direction is the magnetic field? Down. Beneath the wire, what direction is the magnetic field? Left. And to the left of the wire, the magnetic field is pointing up the page. Okay? So here's how we would draw that. Draw a little circle. Okay? Which way did you say the magnetic field is pointing right there? Which way did you say the magnetic field is pointing right there? Which way did you say the magnetic field is pointing right there? Okay. A great multiple choice question is, I show you the magnetic field and I say, hey, which way is the current? Example 3. The thin thing is the wire. What do those dots mean above the wire? Direction. Out of the page. What do those X's mean below the wire? So hold your right thumb in such a way that your fingers curl like that. Now you may want to hold your pen or pencil to represent the wire. You're either, I think, going to hold it like this, or you're going to hold it like this. Whichever one of these matches your fingers in the direction of the magnetic field, your thumb tells you the current. I'm deliberately not modeling this one. Which way is the current going then? Let's see. Because what direction is that? Out of the page? So the only way I can get my fingers to point out of the page up there is this way. Yes? It can't be that way. Which way is the current going? Okay. Until you get good, because my board is vertical, if you want to hold the paper, your paper vertically while we're doing these, you can, but you're going to have to be able to handle every orientation eventually.
I don't understand how we know.
Okay. Okay. Hold your pencil. Okay. Point them that way. Look at your fingers on the top right here. Which way are they pointing above the pencil? Based on this piece of paper here, are they not going into the page?
Oh, they are.
Are they not?
Yeah, they are.
What direction is this? Out of the page.
Out of the page.
Okay? And if I'm flexible, what direction are my fingers pointing now? Underneath. Only way I can do that is my thumb's pointing that way. Okay? If you're really finding that you're having to go all yoga-ish, you're probably doing the question wrong. Now, that's for current, which is which way the positives would move. If you have electrons moving, you can either use your left hand. This is confusing, so I'm going to scribble that out. You know what? You point your thumb in the opposite direction. An electron moving south is the same as a proton or a current moving which way? North. A negative moving east is the same as the positive current moving west. A negative moving to the right, I point my thumb to the left. Is that okay? So here I found this graphic. Here is a picture of the right-hand rule for a wire. We start with this. Then we ask, what about something called a solenoid? If we take that wire and we wrap it around and around and around and around, and you know what? If we make something like this, except compress the wires closer together, because it works better, it's called a solenoid. All a solenoid is a coil of wires. And it turns out what you get then is each of those magnetic fields from each turn of wire overlaps and builds up a really strong magnetic field. This is how you build an electromagnet. Here, really, I'm talking about this. Wrapped really close together, lots of turns of wire. This is a solenoid. Okay? You've probably heard the term and wondered, what's a solenoid? This is what it is. So, if we coil the same piece of wire around and around in many loops, all in the same direction, we call the resulting coil of wires a solenoid. Here's a typical solenoid. Each of those wires has its own magnetic field. Okay? And they overlap. In fact, you get a really strong magnetic field this way. Question. What direction? We're going to talk about that. I should say we can also, it turns out, dramatically increase the strength of the magnetic field by adding an iron core. So if I really wanted to bump this up, it turns out if I put a piece of iron in the middle, I'll get a much stronger magnetic field, even better, because the iron itself also becomes magnetized. Why is this so handy? This allows me to control a pulling or pushing force, because I can repel or attract. I can make it strong or weak. It allows me to turn a magnetic field, a magnet, on or off. This allows me to make things move with current. Where do we use them? All over the place. It has, you know what? Millions of uses. Call this an electromagnet. A magnet that is created with electricity. The question that I asked is, what would the direction of the magnetic field generated by a solenoid be? Turns out there's a right-hand rule for that too. Right-hand rule number 2, the solenoid rule. Here's what you do. You imagine that you're holding the solenoid in your right hand. Okay? By the way, you can see I can either hold it this way or this way. You curl your fingers in the same direction as the current going through the wires. And I'll show you a picture in a second. Your thumb points north. Your thumb points north. We need to practice, we need to try this. Okay. So, it says, what direction is the magnetic field shown below? I didn't give you a solenoid because I also wanted to show you how you draw a solenoid. All right? So, to have a solenoid, first of all, you need a battery or a cell for electricity. We're going to go behind the solenoid. And then to make it look like a coil of wires, once you've drawn that, just watch for a second. What you do is you do long, skinny S's. And that gives you a 3D effect. Yes? There's my solenoid. Write that, copy that. Do your S's the same way as me. So here's a solenoid. Either the left side or the right side is north. How do I figure it out? This is the right-hand solenoid rule. I'll wait till you draw that. Pretty cool, Raj? I know. I'm passing out a distraction, a cool distraction while teaching. I know. Limits. What does the rule say? First thing, label the current. That way. That way. And then I guess I have to use my imagination here, Vikas, but it ducks around behind and it must come up this way. Right? Is that okay? It ducks around behind, it must come up this way. It must come up this way. It must come up this way. You follow it. You have to use your imagination, Dustin. I can't help you with that part. By the way, are you seeing why I said we're going to be doing 3D diagrams? This is part of it, okay? Okay. Hold the solenoid in your imagination, but with your right hand. So first of all of our right hands are either going to be like this or like this. And if you want to, you can hold your paper up vertically with me. I'm going to stand up here. I can either hold it like this or like this. In one of those options, my fingers are curling in the direction of the current. Kohei, you're right. Got to be like this. That's got my fingers going in the same direction of as the current. Which side of this solenoid is north? I'm looking for a word that begins with the letter L. So we would go like this. Yep. By? Nope, because I could have come over the top with my current at the beginning too. There's a zillion different ways to draw these. The magnetic field line would go then like that, like that. No, that's terrible. Magnetic field lines don't cross. Also, going back to your earlier comment, I guess that means that inside the solenoid, the magnetic field points to the left, but outside the solenoid, the magnetic field points to the right. We have to have some kind of frame of reference, so we're going to be worried about the outside. Right here, I'll give you a real basic example. Power door locks. When you move the switch, you're activating a vertical solenoid. You're turning a magnet on. Kathunk! The door lock gets sucked down because you've just magnetized it down. When you want it to go back up again, all that happens is the current flips, which would, instead of a north pole on the top, give you a south pole on the top. Now it repels. Kathunk! Now your door lock goes up. That's the old style door locks that were the up and down kind, which were easy to break into. The newer ones, it's a simple same system, but now it's side to side.
So you
Okay.
get a magnet in the sense of breaking your car. If you did
No, because the issue would be you'd find the magnet would just clump onto the metal of the car first, and you'd have to have a really strong magnet, and then you'd find the irritation was the whole car's made of metal. It's really tough to then also get to that metal inside. I don't think it would work very well. Might. Let's go back to this one. I said we were going to do the direction here. So let me zoom into this one. So turn back half a page. Turn back half a page. Turn back half a page. This one. Well, current flows this way, yes, from positive. And I think if you look really close, it goes behind and it comes, I think it goes this way through the wires. I don't know how good your diagram is, but mine has that. I need to find a better one. Imagine holding the solenoid in your hand. You're either going to hold it like this or like this. Curl your hold it in such a way that your fingers curl in the direction of the current. Is the North Pole the bottom or the top? So you ready, Nick? Ready? Spencer, if I hold it like this, my fingers are pointing against the current, are they not?
Oh, yeah.
Where is the North Pole?
South.
Where? No, the North Pole is not south. Where is the North Pole? On the bottom or on the top? Bottom. Okay. If you can't get the directions, because this unit is vector-based, if you can't get the directions, you're in for some ugly questions. So I'm spending a whole day doing directions, and that's right-hand rule number 2. The solenoid rule. The current rule, you hold the wire, your thumb points in the direction of the current, your fingers curl in the direction of the magnetic field. The solenoid rule, you hold the solenoid, you curl your fingers in the direction of the current, your thumb points north. Or if you know which way north is, you point your thumb in the direction that's north. That tells you which way the current has to flow. We use solenoids in transformers, electric motors, generators, televisions, speakers, doorbells, fire alarm bells. Oh, fire alarms. Our fire alarms are a great example. My friend lives in a very, very old building. It was built in the 1930s. No, that's not what I want. You know what? It's probably not going to work anyways. Let me just see here. I need to type. Old style solenoid alarm bell. All right, let's use a different. First of all, let's pause the video. Here's 2 wires. You know what? I'm going to skip that. Try example 6. Which end will be north, A or B? Try this on your own. Try this on your own. Travis, try this on your own. Okay? Now, normally in the pictures that I give you, Kiowa, I won't put the arrows for the current on it. You'll have to do that yourself. Okay? Which is north, A or B? Okay. The toughest one. Turn the page. Right-hand rule number 3. Okay. Suppose we have a wire carrying a current through a magnetic field. Well, that wire is also creating a magnetic field. It's inside an external magnetic field. The 2 magnetic fields will interact, and the wire will experience a force. The magnetic field will exert a force on the moving charges within the wire, and this, if we're clever, can lead to electric motors. What direction will that force be, Vikas? You're going to put your phone away because I haven't told you yet. Okay? This is the most complicated one. The reason is you're doing 3D vector multiplication. You're doing something called a cross product. But if you take physics next year, your prof will show you this same trick. It turns out you can do a cross product with your hand with a bit of cleverness. Okay? To find, you know what? We're going to use this. If you want to, you could hold your piece of paper up, or you can just follow my board. To find the direction of the force, you point your right thumb in the direction of the current. Here, the current is going that way. And then, instead of having curled hands like we've done for the first 2 rules, you want your hand flat like you're going to give the biggest high five in your life. Okay? So, point your thumb in the direction of the current. You point your 4 fingers in the direction of the magnetic field. This external magnetic field has dots, so which direction is this external magnetic field? What do the dots mean? Okay? Now, Clay, what you can't do is bend your hand. So that's why I'm saying you're going to keep your hand rigid like you're giving a big high five. You're going to instead bend your wrist like that. Okay? Your palm points in the direction of the force. A current moving to the right inside a magnetic field coming out of the page, that wire will get pushed down the page. Down the page. And we're going to practice this one like crazy. Okay. By the way, what you're doing is a cross product, and it turns out that way cross that way is down. Up cross towards you is your right, my left. That way cross up is behind me, away from you. It's a cross product. It's 3D vector multiplication. Oh, by the way, it also this works for screwdrivers. If you want the screwdriver to go in, you turn it this way. If you want the screw to come out, you turn the screwdriver that way. That's actually a cross product as well. It follows the current rule. Learned something new. So in the there we go, down the page. Okay. Here we have a wire. What direction is this wire carrying current? Into the page. What direction is the B field, the magnetic field? To the left? All of you hold your pieces of paper up vertically like this, please, so that you match my board. So what you would do is you would take your right thumb, you would point it into the page. Yes? Which way is the current? So I'm going to extend my hand like I'm high-fiving. I can either go like this, or, you know what? If you're bending weird, Alex, try going like that. Like if you're doing yoga, I'm telling you, if you're doing a yoga, probably there's an easier way to do it. Okay? Is my thumb pointing in the direction of the current? Yes. Are my fingers pointing in the direction of the magnetic field? Yes. Fingers straight. Amelia, don't do this. Don't do this. Wrecks it. You can't add 9 degrees. That's why I'm saying like you're giving the biggest high five of your life. Okay? Which way is my palm pointing? That's going to be the direction that this wire is going to get pushed. So, the first year I taught Physics 12, I had all my students writing their provincial in the library. And I wasn't allowed to be in the room. About halfway through the exam, my phone rang. I picked it up, hello, and the teacher upstairs, nice person, oh, Mr. Dewick, you're going to be so devastated. You're going to be so disappointed in your students. Your students have decided to cheat as a group, and they've come up with these hand signals. They're signaling answers to each other, Mr. Dewick, and I know how much you trust your kids and how hard you worked. Oh, you're going to... And so every year after that, I made sure the teacher knew, look, about an hour into the exam, and also because I don't let my kids do it, I get your hands out. By the way, it is way easier. Get your hands out away from your body. I would tell the teacher in charge, look, they're not cheating. They're not giving each other hand signals. They're doing something called a right-hand rule. Pardon me? No, I explained it to her. Him? I can't remember who it was. Was it a male or female? Anyways, I just, whoops, didn't think of that. But I can prevent that. Let's do another one. Everybody right now underline the word electron. Our rule does not work for an electron. It works for current, which is positive. Which way is this electron moving? Which way am I going to point my thumb? So all of you point your right thumbs to the left. Now this time I'm not going to make you raise your paper up. You can try it on your desk. But I did see someone cleverly, if you're also bending really, spin your paper 90 degrees and it might be easier to get it just because you're, I'm not that flexible. What do those X's mean? Into the page. So you want to extend your fingers into the page. You want to point your thumb to the left. Which way will this electron feel a force? Kevin. So I write it as F for force, B for magnetic field force, because M is taken for mass, is down the page. You can expect like 5 or 6 multiple choice questions along these lines. Heck, I'll even tell you what the answers would be. Up the page, down the page, to the left, or to the right. Yep. Okay. Let's do another one. Example 9. A proton, proton positive, enters a magnetic field as shown. Oh, they didn't give me the magnetic field. Or did they? Magnetic field lines always point from what to what? So let's draw in some magnetic field lines pointing from north to south. Looks like this proton is kind of going away from me, kind of going into your paper. Magnetic field is pointing, now you kind of awkward bend. If I was doing my paper, I would kind of be going like that. Okay, I can do it. Or if I stand up and just put my body on the other side, now that works better. Which way will this proton experience a force? A, B, C, or D? A, B, C, or D? B. 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 Yeah. Oh, by the way, pity the people that are trying to learn this from YouTube, where you can't see me doing any of the pointing. And every year I have a couple of kids. I don't know how to do it. Okay. I'm not that interested in doing that. We got 2 more? No, a few more. Oh, wow. Bunch more. It's okay. We need to practice this. And all the homework is a bunch more diagrams. You should get so good that this becomes a 20-second or a 10-second. Good. Okay. Example 10. The above diagram shows an electron, underline the word electron, traveling to the right. I don't deal with electrons, even though that's the most common charged particle to move around. An electron moving to the right is the same as what? A proton moving which way? To the left. So I'm going to point my thumb to the left. Hey, which way is the magnetic field? Magnetic field lines always point from what to what? You know what? I'll draw one in. So for me, facing my paper, I would go like that. If I stand up in your direction, I would go like that. A, B, C, or D. Sorry? I didn't hear. Yeah. Now, they might write it like that, or they could say as a symbol, right? Number 11. Which of the following diagrams best illustrates the magnetic field lines around a wire carrying conventional current in the direction shown? Okay. This is not the one that we just did because there is not a wire in an external magnetic field. This is asking what magnetic field does the wire itself create? That was a different rule. Which rule was that? Can you see, I think the wire is the middle thing, yes? What direction is the current in that wire? Huh, Jason? Out of the page towards us? Okay. How did we do this one? Whenever they want me to do a wire, this is about the only time where I might say I'll imagine holding my pencil as the wire. Current is coming out of the page towards, and this was the one where you pointed your thumb in the direction of the current. What direction is the magnetic field, A, B, C, or D? Okay. Let's go fast. We're going to go bang, 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 bang. Oh. I think this one's going to be the solenoid rule. This was the one where you imagined holding the solenoid and your thumb told you the North Pole. Let's see. I better add the current. Clay, from the battery, is the current flowing to the left or to the right? Right. Add the arrows. Goes this way, ducks behind, and I think then it's coming out over the top. Yes? Coming from the bottom towards the top. So, first of all, do the right-hand side first. Is the North Pole at X or at Y? I agree. So the first thing I would do is go yes, no, No, and I would even put a north there and a south there. Now, the first column wants the magnetic field inside the solenoid. This comes back to Josh's comment earlier. I got to have a frame of reference somehow. So what we're finding is the magnetic field out of the solenoid, which would go from north to south. But inside the solenoid, which way is it pointing? Yeah. Inside, it's from Y to X. What's the correct answer now that I've done my check marks and X's? Clearly. Okay. I would have known C, not guessed. Guess. Jeez. Here's a wire between. Oh, we have a wire and an external magnet. This is going to be the third one. That hi-fi twisty. Okay. A wire is shown in the above diagram. What would the direction of the magnetic force on the wire be when the switch is closed? Which way will the current flow? Looks like the current will flow this way, this way. Current is going that way. Is that okay, Manny? Which way is the magnetic field? Manny, magnetic field lines always point from what to what? So the magnetic field is going to be going that way. A, B, C, or D. Try this on your own. Don't blur out an answer. Dale, get your hand away from your... Get it out! All right. I got to pause. No, I won't use that. Never mind. A, B, C, or D? First of all, Kevin, no. Okay, that's the biggest mistake. Kids go like this and they add a 90-degree bend and now you've totally changed the direction of everything. Okay, that's why it's, for this one, it's like you're shaking hands, like you're high-fi. Hey! A, B, or C, or D? Okay, Kevin, point your thumb, hold your paper up. Point your right thumb in the direction, no, not paper this way, parallel to this. Point your right thumb in the direction, sorry?
I can't move on, so I'm moving it.
Oh, you can't move? Okay, I'll give you that. That works. A, B, C, or D?
It would be B.
Some uses for this. I don't know if you ever wondered, when we find new mystery particles, how do we figure out whether they're positive or negative? And in fact, later on I'll even show you how do we figure out Q, the charge. Well, for starters, here's a beam of positively and negatively charged particles, and they enter a magnetic field. They would split up. Which ones must be positive? One or two? Let's assume they're positive. Which way are these positive charges traveling when they enter the magnetic field? Point your thumbs to the right, please. What direction is this magnetic field? What do those X's mean? So point your fingers, Jason, into the page. You can do your page or mine up here. Which way will the positives get deflected? Positives, no. Which way would negatives get deflected? If positives get deflected up, which way would negatives get deflected? No, yes. Spencer, what's the correct answer? So I don't know if you ever wondered, like at the Large Hadron Collider, when they're finding these new particles as a basic, how do they figure out whether it's positive or negative? Simple, put them through a magnetic field. Piece of cake. Oh, and later on, we'll also learn that if you know the strength of the magnetic field and you know how much the particles bend, you can calculate the charge. That's a couple lessons from now. Last one, I think, is number 15. Okay. An electron enters a uniform magnetic field as shown below. the path of the electron upon entering the field would be. So first of all, it's an electron. We don't deal with electrons. You can underline the word electron if you want. We're not going to deal with that. An electron moving to the right is the same as a proton moving what? Okay. So we'll point our thumbs to the left. Which way is the magnetic field? Thumb to the left. Which way is the magnetic field? Not meant to be a trick question. Look at the picture. What direction is the magnetic field pointing? Sorry? Can I, you know what? So here's what we're going to learn next lesson, but this is why I snuck this in. It turns out charges will only be affected by perpendicular magnetic fields. Since the magnetic field is left-right, and the charge is also moving left-right, it will not feel any force at all. And the way you know that also is you can't point your right thumbs that way, high five, and also get your fingers point. I mean, you kind of try and smoosh your hand. That's not what I said. High five like you're shaking hands. Your homework, I apologize. I have to give you homework for this long weekend to give you next weekend off. I gave you a bunch of right-hand rule questions. I got a cool video or two to show you.